Everything that we've done so far has involved one variable at a time, so you end up with one measurement for each individual in the sample. The rest of what we're going to cover in Chapter 2 is what happens if you deal with two variables at a time, more specifically two quantitative variables, and you have two measurements for each individual in the sample. When you have two quantitative variables measured on each individual in the sample, the type of graph that you would end up with would be a scatter plot, where you've got two measurements for each individual, one for the x variable, one for the y variable, and you can plot the points in the scatter plot like you would plot points in a Cartesian plane. Once you have the scatter plot, the first thing to look for would be if there's any kind of a trend. Those first two that are on this screen, positive and negative association, they work the way that slope works. So if the scatter plot trends upward from left to right, that's when there's a positive association between the two variables. If it trends downward from left to right, that's when you have a negative association. If there's no pattern visible in the graph, that's where you have no association between the two variables. There are a lot of cases where you can anticipate the type of association that you're going to have even before the scatter plot's constructed. For these four pairs of variables, we kind of already know what we're going to get. Weight versus city miles per gallon. Generally you think, well, bigger, heavier vehicles are going to have a lower value for the miles per gallon. They're going to be less fuel efficient. So you expect to get a negative association there. The next one, weight versus fuel capacity. Bigger, heavier vehicles are going to have larger fuel tanks. They should have more fuel capacity. So you expect a positive association between those variables. The third one, page number versus fuel capacity. The page number really doesn't have anything to do with the vehicle itself. So here, intuitively, you expect there to be no association at all between those variables. And the last one, acceleration time versus quarter mile time. Those are directly related, and certainly you'd expect a positive association there. As we saw in that example, there are a lot of cases where you can anticipate the direction pretty easily, but trying to anticipate the strength is difficult. It would be nice if there was a way to quantify that. That's what the correlation does. The correlation, like it says there, is a measure of the strength and direction of a linear association between two quantitative variables. Really, it's a measure of strength, and you kind of get the direction for free. We'll see that on the next slide. The notation down below, the sample correlation is denoted by a lowercase r, population correlation is denoted by a lowercase Greek letter rho, which unfortunately looks a whole lot like a lowercase p, which we also use as notation for a population measure. That's kind of unfortunate, but that's the accepted notation and we just have to kind of work with it. Correlation properties. The first thing is that the possible values are between -1 and +1 inclusive, although in reality you don't see the -1 or +1 very often at all, if ever. Because in order to get one of those extreme values, you need all of the points in the scatter plot to be lined up in a perfect linear arrangement. That's not a thing that you see in real life a whole lot. Number two, this is where you get the direction for free, where the sign of the correlation matches the direction of association. So if you have a positive association between the variables, you're going to have a positive correlation and vice versa. Same thing with a negative association and a negative correlation. If there's no linear association between the variables, you'll get a correlation that's close to zero, but probably not exactly zero. To get a correlation of exactly zero, typically you need a perfect geometric shape to pull that off, so that's probably not what you're going to see in real life. But if you have a scatter plot with no discernible pattern, you'll get something that's very slightly above or very slightly below zero. That's what you'd anticipate there. Point number 3 is a consequence of point number 2. The closer the correlation is to zero, the weaker the linear association between the variables. And then the farther the correlation is from zero, the stronger the linear association. So farther away in either direction, that's easy to pick up on for the positive values, but that works for the negative values too. So a correlation of -0.8 is stronger than a correlation of -0.3, that kind of thing. The formula for the correlation that's there in number 4, you're never going to have to compute it from scratch. That's just there for two things, one of which is to point out how the correlation has no units. The z sub x and z sub y are z-scores. Basically what you do to compute the correlation from scratch is that since every individual has two measurements, one for the x variable and one for the y variable, you can standardize both of those measurements. And then for each individual you multiply the z-scores together, and then that capital sigma for summation means that you have to add all of those products together for every individual in the data set, then you divide by n minus 1. The whole point here for why I have this on this slide is that the correlation is based on z-scores, and z-scores don't have units. Because when you divide by the standard deviation to compute a z-score, you're dividing the units out. So if the correlation is based on z-scores and z-scores don't have units, the correlation doesn't have units either. The other reason for having that formula in there is 0.5. Basically, the reason that 0.5 works is because if in that formula in that box under number 4, if you interchange the order of z sub x and z sub y, you'd end up with the same thing. Now we have scatter plots that go along with the associations that we were talking about earlier. Weight versus city miles per gallon, we said we anticipated something negative. That's certainly what we're getting. We're getting negative 0.91, so that's a pretty strong negative correlation. That's pretty close to negative 1. I guess the one other thing I want to point out here is if you did draw a best fit line through that, you can get a pretty good idea of where it would go just by looking at the scatter plot. Typically when that happens, you've got a pretty strong linear relationship. That's what's going on in number 2 as well, except that it's positive. Weight versus fuel capacity, we said we expected that to be positive. It certainly looks like that's what we're getting. The correlation's 0.89, pretty close to 1. And if you look at that scatter plot, it's pretty clear where the best fit line would go and that it would be increasing from left to right. Page number versus fuel capacity, there we expected no association. That's what we're getting. If you look at the scatter plot, there's really not much of a pattern there at all. So we should get a correlation close to 0. That's what we've got. We've got a correlation that's a little bit less than 0, but pretty close. Number 4, where the two variables were directly related to each other, not only is that positive, but that's very linear. We've got a correlation that's almost 1, and if you look at where the best fit line would go, the points in the scatter plot are really tightly wrapped around that line. So that's very, very linear, and we're seeing that in the correlation where it's so close to positive 1. You can find the correlation using StatKey. The option that you want is in the lower left of that upper part of the home screen for StatKey. Under Descriptive Statistics and Graphs, what you want is 2 quantitative variables. On this slide, we have an example, and then what happens when you feed that example data into StatKey. We have data for 8 years where we have the number of forest fires in a year and the number of acres burned. The way that you enter the data into StatKey, and you don't need to have the header row like I have in there, but what you would have to do is you have to put every individual in a single row, where it's X measurement, comma, Y measurement. So for the first year, we have 72 fires, 62 acres burned. The way that would be written is 72, comma, 62. There's the first year. Then the second year is 69 and 42, so the next row 69, comma, 42, and so forth. After you enter all the data, the summary statistics are really the important thing. The biggest part in StatKey is going to be the scatter plot with the best fit line. That takes up most of the screen. But the important thing is toward the right where it has the summary statistics. And for right now, the important thing is correlation. And you can see it right there in the table. It's 0.771. The whole point of having this slide in here is to show the effect that outliers can have on the correlation. Both of these scatter plots are standardized penalty yards versus uniform malevolence rating for NFL teams. This is an example from our textbook. I think this data is pretty old, about 30 years old, but it'll still work. So if you look at the one that's on the left, that scatter plot, there are a couple of outliers in the corners, in the lower left and the upper right. Those are removed in the scatter plot that's on the right side. And look at what happens to the correlation. It goes from 0.43 to 0.08. Just looking at what the two variables are, you think, I don't know if there's really going to be much of an association there. So the correlation for the scatter plot that's on the right is probably going to be more in line with that intuition than the correlation that's on the left. But the main thing here on top of that is the huge effect that those two outliers are having. Those two outliers are making that data look a whole lot more linear because they kind of line up with each other in a way, since they're at opposite corners. And that's having this huge effect on the correlation. So that is a possibility that outliers can have a big effect on the correlation. So that's a thing that you have to watch out for. Correlation really only measures the strength of a linear association between variables. So it's possible to have a weak correlation, but to have a clear pattern or a clear trend between the variables, just one that's nonlinear. If you look at what's going on here, where it's temperature versus month, where month is written quantitatively as 1 for January, 2 for February, and that kind of thing. If you did this for several years instead of just one, it would kind of resemble a sine wave, where it would go up, then down, then up, then down, then up, then down. That's a clear pattern, but it's nonlinear. And that's the whole point here. It's possible to have a scenario where there is a clear association between the variables. It's just not a linear association. And in that case, you will get a correlation that's close to zero because the correlation only measures the strength of a linear association between the variables.